The energy of a bond indicates its strength and is measured as the energy required to break the bond.
This table in the upper right are literally the energies required to break those types of bonds. So if you start in the upper left, a CH single has 413 kilojoules per mole to break up, carbon-carbon single bond 348, etc., etc. That's kind of interesting. But notice here how you can make some connections. So like the CC, the first one we just talked about, that's a carbon-carbon single, a bond order of 1. And if you go down here a little bit farther, here's a carbon-carbon bond order of 2, a double bond. And here's a carbon-carbon triple bond order of 3. So notice the energies are going 348 to 614 to 839. The energy required to break them is going up as bond order goes up. So when it comes to bond energy and bond order, we say that as bond order goes up, the bond energy, the energy required to break the bond, also gets larger too. And you'll see that for lots of different things. You can also do that for carbon-oxygen. It goes from 358 to 799 to 1072. Now notice it's not like exactly 2 times the single bond equals the double bond. It's not quite that simple. But we can say on a relative scale that as your bond order goes up, the bond energy, the energy required to break the bond, goes up as well. But remember too, as your bond order goes up, the bond length goes down. It's a really interesting thing. So that's why, again, bond order goes up, bond energy goes up, but bond length goes down. Oxygen, dioxygen, has a double bond when you draw out its Lewis structure. It has a 498 kilojoule per mole energy, and the length between the oxygen atoms in an O2 is about 121 picometers. Now, hydrogen peroxide, H2O2, when you draw out its Lewis structure, oxygen-oxygen single bond. Notice the bond length, all right? We went from a bond order 2 and O2 to a bond order 1 and H2O2. Bond length got larger, so bond order went down, bond length goes up. On the other hand, the bond energy went from 498 kilojoules per mole to just 210 kilojoules per mole. So bond order went down, the energy required to break the bonds went down too. So remember, bond order goes up, bond energy goes up, bond length goes down. Ozone is O3, and ozone is a resonating structure. It goes double on one side and single, then it goes double on the other and single on the other. Notice how the bond length is between the double and the single bond orders, all right? And that makes sense because the bond order for ozone would be the 3 bonds divided by the 2 places it can go, bond order 1.5. And if you had to make a guess as to the bond energy, you'd say it was between 498 as a high and 210 kilojoules per mole as a low, somewhere between them. Now I'm guessing because the bond length is much closer to the double than the single, I would guess that the energy to break ozone would be somewhere closer to 498 than 210. But that would be the best guess I could do. We should look that up or, of course, do it in experiment and stuff to figure it out. You can use those bond energies in some kind of cool ways. So let's say you wanted to figure out the energy of this reaction, which is H2 plus Cl2 making 2 HCl. Well, you can use those bond energies to actually figure this out, which is really cool. The net energy, the delta H, remember delta H is the sign for enthalpy. Enthalpy here is the energy required to break bonds minus the energy evolved when bonds form. So here's kind of the punchline that I like to use. I like to use that the energy equals bonds broken minus bonds formed. And in a reaction like this one, what you're going to do is you're going to break the HH bond and you're going to break the Cl-Cl bond. But then you're going to form 2 HCl bonds. So these are the numbers from that table we saw earlier. Bonds broken would be the HH plus the Cl-Cl bond. And then to figure out bonds form, minus 2 times this number right here. It's pretty cool. You never have to memorize any of those numbers.
Hydrogen and chlorine react to form hydrogen chloride. Because the total energy of the broken bonds is less than that of the bonds formed, the overall reaction is exothermic,
So the video there just said that it's exothermic. Exothermic means the delta H value will be negative. A positive delta H would be an endothermic. That means energy has to be given in. But let's confirm it. Let's confirm that it really is an exothermic reaction. So again, it's bonds broken minus bonds formed. So if you add up the bonds that you're breaking, that's HH and ClCl, that comes out to be 679 kilojoules. That's the bonds broken. Now bonds formed, we're forming 2 HCl bonds. So 2 times 431, the value there is 862. Then finally, bonds broken, 679, minus bonds formed, 862, that comes out to be negative 183 kilojoules. So sure enough, this is an exothermic reaction. Energy is given off when the HCl is made.